Okay, this is going to be a longer video as we go through the review of all these triangle relationships. So let's go problem by problem, and we'll start now with finding the missing parts in the triangle below. It's a right triangle. We know one angle is 71.5 degrees, so our missing angle is the easiest to figure out, and that's going to be 18.5 degrees. Is this angle right here. Okay, so we've got our three angle measurements. What we're missing now are our side lengths. Let's start with our hypotenuse. Since we're given angle 71.5 degrees, let's use that to try and find our hypotenuse, which is right here. The 15 is our opposite side. It's opposite of our angle 71.5. So the trig function we're going to choose to use in order to figure out the hypotenuse, knowing the opposite, is the sine function. So the sine of our angle 71.5 degrees is going to be the ratio of the opposite, which is 15, over our hypotenuse, which we don't know. So what we need to do is solve for the hypotenuse by dividing 15 by the sine of 71.5 degrees, and that answer is 15.817 if we round to 3 decimal places. So we've got our hypotenuse, 15.817. Let's go and find the missing leg, and this is our adjacent side. So we were given the opposite side, and we were given our angle 71.5. We want the adjacent, so the trig function using opposite and adjacent is our tangent. So let's use the tangent of 71.5 degrees is the opposite, 15 over our adjacent. Solving for the adjacent, we're going to have to divide 15 by the tangent of 71.5 degrees, and that answer is 5.019. And we have our side lengths and angle measurements. Okay, another example here, right triangle. We know one angle there is 42 degrees. The other angle is going to be 48 degrees. All the angles should add up to 180 degrees, so this missing angle here is 48 degrees. Now if we stick with the given angle 42, where it's located, 1.2 here is our hypotenuse. We're missing the adjacent, and we're missing our opposite. So what we need to do for side lengths is to find the adjacent and the opposite. Let's start with adjacent. The trig function that relates adjacent and hypotenuse is going to be the cosine. So the cosine of our angle 42 degrees is going to be our unknown adjacent side divided by the hypotenuse, which is 1.2. And that's going to get us an adjacent side of 0.892 if we round. We've got our adjacent side. Now for the opposite side, it's not the cosine that we want, but it's the sine function. The sine of 42 degrees is the ratio opposite over hypotenuse. Solving for the opposite here, we're going to end up with an opposite side length of 0.803. And we've solved that right triangle. Okay, example 3 here comes without a diagram, so the best thing to do first is to draw yourself a picture. So triangle ABC, where angle C is right, angle B is 81 degrees, and AB, side length AB is 22.5. So we want a triangle. Here's a triangle ABC. C is our right angle. Angle B is 81 degrees. And side length AB, which is the hypotenuse, 22.5. Okay, so this is going to be similar to our previous example where we know an angle measurement 81 and we know the hypotenuse 22.5. We don't know the adjacent side and we don't know the opposite side again. And of course the easiest is to start with the angle measurement. So this angle A has to be 9 degrees. so we know angle A. Let's again start with our adjacent side. So the cosine of 81 degrees is our adjacent over our hypotenuse, which gives us an adjacent side length of 3.520 if we round. And again, our opposite, we're going to stick with the sine function, the sine of 81 degrees, and that's our opposite over hypotenuse. So the opposite side length is 22.223, again if we round. So we've got our angle measurement and our two side lengths. Okay, let's start out number 4 like we did before, where we're drawing our own right triangle. Triangle ABC, C is the right angle. So here's triangle ABC. ABC, C is the right angle. Now we're given two we're given two side lengths. AB is 11, that's our hypotenuse. Side BC is 5.5. And we want to solve for all missing side lengths and angle measurements. Well, knowing two side lengths, the third side length, we're going to use the Pythagorean theorem. So our missing side length AC squared plus 5.5 squared, which is our other leg, BC, should equal our hypotenuse squared. So solving for AC is going to get us 9.526 is our side length AC. Okay, now we've got all three side lengths. How do we go about finding the angle measurement? Well, let's start out with angle A. If we call angle A, we call that theta, and we know in relation to theta, we know the opposite is 5.5, and we know the hypotenuse is 11. The sine function, the sine of theta, is the ratio of the opposite, 5.5, to the hypotenuse, 11. And here we can use the inverse sine function to solve for the missing angle theta. And when we do that, we get theta equals 30 degrees. Well, now that we know theta is 30 degrees, which is angle A, angle B, the measurement of angle B has to be 60 degrees because we're in a right triangle, 30, 60, 90 right triangle. Problem number 5, triangle ABC. Same scenario here, A, B, and C is the right angle. BC has a length of 3 and AC has a length of 4.2. So now we know the two legs. Our hypotenuse here is going to be our Pythagorean theorem. We're going to do 3 squared plus 4.2 squared, and that's going to equal our hypotenuse AB squared. So again, solving for AB, that hypotenuse length is 5.161. Clearly our longest side, the hypotenuse has to be the longest side. Taking a look again at our angle measurements, if we look at angle A, and we call angle A theta, or we'll do this one without theta, we'll just call it angle A. We know that in relation to angle A, 4.2 is the adjacent, and we know 3 is the opposite. So the trig function for angle A that involves the opposite and the adjacent is the tangent. So the tangent of A is the opposite over the adjacent. Well, we can use the inverse tangent then to solve for A, and that's going to get an angle measurement of 35.538 degrees if we round. Now again, we can subtract that from 90 to get our missing angle B, the measure of angle B, and that's going to give us the approximate value, since we rounded angle A, the approximate value of 54.462 degrees. We've got our angle measurements, we've got our side lengths. All right, now tree's shadow is 15 feet long when the angle of elevation of the sun is 67 degrees. Find the height of the tree. So let me do my best drawing of a tree here. And we know that the shadow of the tree, here's our shadow of our tree. All right, not bad. So there's our shadow, there's our actual tree. We're told that the shadow of the tree, which I'll mark here in red, is 15 feet long when the elevation of the sun is 67 degrees, is our angle here, 67 degrees, whoops. Find the height of the tree. This is what we're after right here. This is our height h over here. What's the height of the tree? So in relation to the angle of elevation, 67 degrees, h is our opposite side. And we know 15 is the adjacent side, adjacent to the angle. So the trig function we're after is the tangent of 67 degrees. That is the ratio of the opposite, which we're calling our height h, to the adjacent 15. So plugging that in the calculator, we get the tree to have a height of 35.338 feet. All right, similar problem, but now the Washington Monument. It has a height of 169.29 meters, and at one particular point in time casts a shadow 201.2 meters long. Find the angle of elevation of the sun at the time. So here's my best Washington Monument picture. I think there might even be a few windows at the top there. Here's my window. Got maybe some people in there celebrating summer vacation, taking a trip to DC. All right, so there's the Washington Monument. Here's the shadow of the Washington Monument. It's actually a little bit longer than the monument itself, so I'll make it, yeah, here it is, okay. There's the shadow. So we will give the shadow a length of 201.2 meters. The actual height of the monument, 169.29. And our question is to find this angle of elevation. We'll call it theta. What's the angle of elevation of the sun at the time? That sun's creating the shadow, so that's the angle. Well, the shadow is our adjacent side. Again, just like the tree, the height of the monument is our opposite side. So the tangent is again going to be the trig value, or the trig function that we're after. The tangent of theta is our opposite divided by our adjacent. And it's going to be the inverse tangent that we want to use in order to solve for the missing angle. And when we do that, when we plug in the inverse tangent of 169.29 divided by 201.2, we get an angle measurement of 40.077 degrees. Okay, now we're going to look at three given side lengths and determine whether it's not possible or not to construct a triangle with the given side lengths. Here's what we're really after. What we need is, we need the shortest side, in this case 6. We need 6 to be greater than the difference between the two longer sides. So the 11 minus the 7, which is 4. 6 is certainly greater than 4. Fantastic. Okay, and we need the longest side, 11, to be less than the sum of the two smaller sides, 6 plus 7, which is 13, and 11 is certainly less than 13. So this could be a triangle. Yes, it is possible for this example number 8. Okay, 8 looks good. How about number 9? Our smallest side, 3. Is 3 greater than the largest minus the middle, which is equal to 3? And the answer is no. they're equal, but the smaller side 3 is not greater, so this immediately we know cannot be the side lengths of a triangle. And number 10, okay, this looks pretty good to start out with. 28 is certainly larger than 39 minus 34, which is just 5. So that looks good. And 39 is it less than the sum of 28 plus 34, which is equal to 62. 39 is less than 62, so perfect. That could be a triangle. Okay, number 11 here, we've got a triangle ABC. The measurements of angles A and B are given. We want to rank the sides from smallest to largest. There's no mention of a right angle, so let's just draw our triangle here. Angle A, angle B, and angle C, triangle ABC. A is 112 degrees, okay, not drawn to scale, obviously not. Angle B is 32 degrees. In order to determine the ranks of the sides, we really need angle C. So let's figure out what angle C is. If you plug 112 and 32 into the calculator, subtract it from 180, angle C has a measurement of 36 degrees. So the shortest side is opposite from the shortest angle, or the smallest angle. So if we're going to rank our sides from smallest to largest, the smallest angle is B, so AC is the shortest side. Okay. Follow that by the middle angle, the angle that's in between, and that's 36, so the side opposite that is side AB. And then the largest side is across the largest angle, so that the largest side is side BC. Okay, find the missing sides in the special right triangles and write your answers in simplest radical form. Here we've got a 45, 45, 90 right triangle, and the hypotenuse here has a length of 2 root 2. Well, we know in a 45, 45, 90 right triangle that the hypotenuse is root 2 times the legs. So that is a simple calculation to tell us that the legs both have a length of 2. Okay, how about finding the side lengths here on these two other examples? The first one's a 30, 60, 90 right triangle. We're given the hypotenuse here is 24. The short leg, which is BC, is half the hypotenuse. So that one's easy, that's 12. And then the long leg, AB, is always root 3 times the short leg. So that's going to be 12 root 3. Now in number 14, the diagram, it doesn't indicate that this is a 30, 60, 90 right triangle. All we know is that this angle is 60 degrees. So technically speaking, we would need to use we wouldn't be able to conclude what the side lengths A, B, and C are just from what we know in just this diagram. But let's draw in the notation that this is a right triangle. This is obviously a 30-degree angle up here, 30 degrees. And we know the short leg is root 3. So the hypotenuse AC is always double the short leg. So that's 2 root 3. And then the long leg is always root 3 times the short leg. Well, what's root 3 times root 3? That's just 3. So we've got those lengths there. Okay, in a triangle ABC where angle B is right, given the sine of A is 4/5, find the tangent of C. So again, let's draw ourselves our triangle ABC. Now this time it's B that's the right angle, so triangle ABC. Angle B is the right angle. We know that the sine of A is 4/5. Well, what that tells us here, the sine of A is 4/5. That ratio is the ratio of the opposite to the hypotenuse. That's what the sine ratio is. So the 4, we can actually label our diagram. The 4 is the opposite side of A, and then the 5 is the hypotenuse of the triangle. That's going to give us the information that we need in order to figure out the tangent of angle C. Now the tangent of C, requires knowing the opposite of C here, C. We need to know the opposite of C, and we need to know the adjacent of C. Well, we know the adjacent, we just don't know the opposite. But when you know two side lengths of a right triangle, you can figure out the third with the Pythagorean theorem. So the missing side length, AB squared plus BC squared, the two legs squared and added together, should be our hypotenuse squared. Well, plugging that in, or recognizing that this is a 3, 4, 5 right triangle, our opposite side needs to be 3. Now that we know the side lengths, coming up with the tangent of angle C is just as simple as writing the ratio of the opposite over the adjacent. And there's our tangent of angle C. Okay, classifying these triangles as right, acute, or obtuse has to do with identifying the longest side and seeing with the squares of the two shorter sides added together, how does that compare to the square of the longer side? And in this case, we're going to square 9 and add it to 12 squared and compare it to 15 squared. And we get 225 on the left, we get 225 on the right. If these are equal, that tells us that these are the side lengths of a right triangle, because a squared plus b squared equals c squared. Now, in this second example, number 20, here's our longest side, 14, so we want to compare 10 squared plus 11 squared. How does that compare? Put a question mark there. Put a question mark. How does that compare to 14 squared? So 10 squared plus 11 squared gets us 221. 14 squared is 196. So the two shorter sides squared and added together is greater than the length of the third side squared. And when that happens, we have an acute triangle. And this third example, here's our longest side. Okay, our other two sides, 8.2 squared plus 4.1 squared. How does that going to compare with our longer side, 12.2 squared? Well, our 8.2 squared plus 4.1 squared is 84.05. 12.2 squared is 148.84, and that's the greater value. So no big surprise, our first example was a right triangle, second example, an acute triangle. When the longest side squared is greater than the other two squared and added together, of course we have an obtuse triangle.